We've talked so far about resistance and capacitance, and now that we've learned Faraday's law, we can look at the last piece of the puzzle, which is inductance. Here in the picture below, we have a current I1 in this coil number 1, and it creates a B field B1. That's going through this coil number 2, and it's causing a flux, and that's labeled phi 21 in coil 2. If we had a current in coil 2, that would cause a flux phi 12 in coil 1. This interaction between the two is called mutual inductance. It depends on the geometry of the coils and their orientation to each other and their distance from each other. And it turns out that by symmetry, the inductance of coil 2 with respect to coil 1 is the same as the inductance of coil 1 with respect to coil 2. Your book uses M21 and M12. We're not going to bother with it because they're both equal to the same thing, which we just call M. And that depends on, for example, the number of turns in one divided by the current in the other. And this flux between them is the linking part. Now, the units of inductance are henries. Again, this is a name, so it's a capital H. 1 henry is a pretty large inductance. The thing that's a little bit more interesting to us than this formula is the EMF developed in one coil as a result of a changing current in the other coil looks like this. EMF in one is negative M di2 dt. Now, eventually we'll get to transformers that are a huge part of the grid, and there we want a very large value of M. We want two coils to be very tightly coupled to each other so that changing the current in one gives us the maximum possible EMF in the other one. If we want to do things like charge batteries without electrical contacts, like electric toothbrushes have done for years, or new wireless chargers, we again want a large M there. We want a linkage between these two coils that's not physical wire. There are other times where we don't want a large value of M. In general, though, we're going to treat it, we're not going to do much with it, but we're going to treat it kind of like we did for static friction. It's much easier to measure than to try and calculate it from first principles, because this, again, like some of the other integrals we've seen, this would really be, in general, a horrible thing to try and calculate, this mutual inductance. It's much easier to just measure it. Now, what we'll deal with a lot more often, one coil's current can affect another coil, but the coil can also affect itself. This is known as self-inductance. We use an L for that, and we just use this way, way more than mutual inductance. This is again measured in henries, and here the flux in the circuit depends on the current it carries and the self-inductance. So if we have N turns and phi is our flux, that product of those two is going to be equal to inductance times I. Now, just like we had V equals IR for resistors and Q equals CV for capacitors, our key equation for inductors is the EMF is negative L di dt. The negative sign means this inductance is going to try and oppose whatever the change in the current may be. So this picture below from your book, if we have an increasing current going to the right, it's going to be like we've put a little battery in the circuit, and notice the positive side here is on the left. It's going to try and push back against that increasing current. On the other hand, if we have a decreasing current to the right, the induced EMF is going to try and oppose the decrease, which means we have the positive side of this little imaginary battery here on the right. The inductor acts like a battery pointing to the right to keep that current up. This, by the way, is the symbol for an inductor in an electrical schematic. It's just a few curly loops here. This EMF is trying to reverse whatever change is happening, and in that sense it acts like inertia, which is mass, from last semester. Mass doesn't resist velocity, but it resists changes in velocity. So it's hard to get something, a heavy truck, moving when it's stopped. It's hard to stop it once it's moving. Now, just like we found the key equations for the behavior of resistors and capacitors, and then found the sort of construction equations for them if you wanted to start a factory, we could write a construction equation for the inductor as well. If we have a solenoid, we already know this part. The magnetic field is mu naught times turns per meter times the current. The flux would therefore be B times A, so we could write that as mu naught NA over length times I. We could then use our relation from above, N phi equals Li, and rewrite this a little bit. We could say L of the solenoid is N phi over I, but that has to be equal to this, mu naught N squared A over the length. If we want to multiply by by length on top and bottom, which seems like a weird thing to do at first, but it gives us an L squared on the bottom, and on the top it gives us the volume. So we can write this as mu naught little n squared times the volume for the inductance. We could make a much better solenoid using iron instead of a vacuum, because mu for iron, the permeability, is much greater than permeability of free space. If you were a kid and made a electromagnet by wrapping a wire around a nail and then connecting the ends to a battery, you might have experimented, do I need the nail? And if you did, it makes a big difference to have the nail there, because then you have this value that could be thousands of times the vacuum value, making it a much better magnet. Now, the energy in an inductor a lot of times is compared to kinetic energy, since we have to have motion, we have to have a current. We can figure out this energy by using P equals IV like we've done before, and energy is integral of power over time. So we write this, our current is I, our EMF we saw earlier, L di dt. We do this integral, and of course in physics we can treat these things like fractions and multiply them, cancel them. We get L integral of I di, which is a pretty easy integral, 1/2 Li squared. If we want the energy density, we can divide this by the volume. We want to make that easy. We can replace L with the formula for a solenoid's inductance, and we get this, 1/2 mu naught turns per meter squared times current squared. Now, since we already know that B is mu naught Ni, we could also write this as just B squared over 2 mu. So just like we had a form for the energy density of a capacitor that involved the electric field instead of capacitance and voltage, we've got a form for energy density here that involves the magnetic field. This is even less, the energy storage capability here is even smaller than for capacitors. For a 1 Tesla field, which is pretty significant, over a cubic meter, which is a very large region to establish that field in, the energy density would only be about 400,000 joules per cubic meter. It would be hundreds of times that for a capacitor and thousands of times that for lithium-ion batteries. This inductor's resistance to changes in the current, how does that affect a circuit? Well, here on the left we have a relatively simple circuit. We've got an inductor, a resistor, and 2 switches. One will add a battery to the circuit, and then if we flip them, we'll take the battery out of the circuit. So the first thing we do is forget the bottom and just close this switch S1. Here we have the battery trying to establish a current through the inductor and the resistor. If not for the inductor, we would say we instantly get a current E over R. But with the inductor present, it doesn't want to see the current change from 0 to E over R, so it fights that change by acting like a battery pointing the other way. And what this means is it takes a while for that current to build up. Once, after we leave this for a while, and we'll see below what a while means, after we leave it going for a while, then we flip the switches. We break this one to take the battery out of the circuit and close this one so that there's still a path for current. And what we find is now the inductor is acting like a battery again, only pushing the current in the way it was going, the way that the battery had it going. The inductor does not want to see this change either, so it tries to continue running a current this way through the resistor. Now, how do we figure this out? How do we do something useful with it? Well, our fundamental inductor equation, EMF is L di dt, tells us an instantaneous current change would give us an infinite EMF. So that won't be possible. And what we'll know is, as soon as we close this switch or open this switch, instantaneously we don't have a change in the current. It can start to change, and we'll see what that formula is, but infinitesimal time after we close the switch, nothing happens. Now, we could use Kirchhoff's loop rule to go around this middle figure, this circuit, and we'll get EMF of the battery minus LdIdt minus IR equals 0. And as you probably expect by now, this is really a differential equation. It's essentially, to a math person, they'd say this is the same one as for the RC circuit. We just have different variable names. So here our solution is the current as a function of time is battery voltage over R times 1 minus e to the negative RT over L. Here we're going to define an inductive time constant instead of the capacitive one we had before. That's L over R. And what it tells us is the current doesn't instantly jump from 0 to this, but it builds up over time, just like the charge in an RC circuit. Now, what happens when we open switch 1 and close switch 2? That means move to this figure. Now we don't have a battery in the circuit, but again, the current can't stop instantly. It keeps flowing, dragging kinetic energy out of the inductor. Here, Kirchhoff's law is just this, LdIdt plus IR equals 0. And our solution is our initial current decays exponentially, e to the negative t over tau L. Now, once you know this, if you now know that an inductor and a motor are both essentially just big coils of wire, there's something that happens that's a little bit easier to understand. If you pull the plug of a running motor out of the wall like a vacuum cleaner, instead of using a switch to turn it off, and this is kind of hard on the equipment, so you shouldn't do this, but when you pull the plug, the current goes from whatever it was to 0 very quickly. That means di over dt is very large. And L is already large for this motor or inductor, so we get a very large induced EMF from our key equation. So this term, the di dt is large, the L is large, that means the EMF is very large. So if we have a very large EMF, what we can have is dielectric breakdown. So we pull the plug and it can be high enough, the electric field can be high enough to exceed the breakdown strength of air, and we get a spark.